Hello, our final year project is based on the topic of current status and future trends of indium gallium arsenide, indium aluminum arsenide on indium phosphide substrate using high electron mobility transistor introducing the breakdown voltage under the guidance of Professor Bijoy Goswami. Our group members are of four, namely Akash Burman, Debashish Das, Rupak Sharma, and Lonkim Intikathar. Our project is based on device simulation of high electron mobility transistor HEMT to get the desired IV characteristics. And our designing is done on TK-Tech build and simulated on Tony plot. The transistor is made up of different compound semiconductors, that is indium phosphide, aluminum gallium nitride, indium gallium arsenide.
So here is an abstract of our final year project. The high electron mobility transistor or the HEMT devices are the competitors with a substitution previous field effect transistor or FETs with amazing performance at high frequencies and improved power density with satisfactory potency. Our work concentrates on designing and simulating the indium gallium arsenide, indium aluminum arsenide, and indium phosphide HEMT by using TK simulation software and evaluating the drain current and breakdown voltage performances. Coming to the next slide, we have got the previous work update. That is the work that we have done previous, but the result was not that much satisfactory. Here we can see the previous structure or the structure we have made here earlier. Here we have used indium phosphide as a substrate and indium gallium arsenide as the buffer layer with indium aluminum arsenide as the channel layer and SiO2 as the oxide layer. Here the length of the gate is 50 nanometers. The spacing between the gate and source is 0.1 micrometer and the spacing between the gate and drain is 0.6 micrometers. But there are still some inherent flaws to the structures which led us to the modification of the structures, which are in the upcoming slides and be explained by my friend Rupak.
Previously the HEMT structure was made up of three layers, that is substrate, buffer layer and channel. The problem with previous structure with three layers and the electrodes ranging from oxide layer to substrate was that the band gap difference which deviates from the ideal HEMT band gap, because of which the breakdown voltage becomes greater than expected. Hence the structure has been modified by putting more layers, that is cap layer and more buffer layers, and by shortening the length of electrodes.
Now I am going to explain about our final work. As Rupak mentioned that there are some problems in our previous structure because of which we cannot achieve our goal regarding bandgap curve and breakdown voltage. So we have introduced aluminum gallium arsenide layer as a spacer layer, indium gallium arsenide as a channel layer, and gallium nitride as a cap layer below the electrodes. We have also reduced the length of the electrode to 0.01 mm that are source and drain and 0.02 mm gate. We also changed the work function to copper on source and drain and gold on gate, as you can see in the code. So this is our overall code. Now if we run the code, it will take some time to compile. This is the structure, and here we have the electric field curve, and this is the more accurate bandgap diagram, and as you can see the bandgap is reduced in the position of gate terminal, results maximum electron flow from valence band to conduction band. So that's all in the video, and thank you.